It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we stood at the very dawn of an idea. We were in the halls of Dartmouth College in 1956, where a small group of brilliant, ambitious, and perhaps slightly naive researchers coined the term artificial intelligence. They launched a field on a wave of pure optimism, armed with new digital computers and a profound belief that human-level intelligence was not just possible, but solvable, perhaps within a few decades. That optimism, that spark from the Dartmouth workshop, didn't just stay in a New Hampshire college. It ignited a wildfire. It lit up research labs, captured the public imagination, and most importantly, opened the checkbooks of government funding agencies. This period, stretching from the mid-1950s to the early 1970s, is what AI historians call the golden years. But today's episode isn't just a story of success. It's a story of a cycle of incredible hype, astonishing early results, and the hubris that follows. It's also the story of the inevitable collision with cold, hard reality, and the crash that follows that collision. We are talking about the AI winters. If you are just joining us on this journey, I highly recommend you start with episodes 1 and 2. Our goal here is to build a university-level curriculum, and just like in any good course, each lecture builds on the last. Today, we're exploring the dramatic history that shaped why we're going to study classical AI first. So, our learning objectives for today are threefold. First, we will explore the golden years. What was actually built during this time? What were these early programs that got everyone so excited? Second, we will dissect the first AI winter. We'll be detectives, examining the evidence, the reports, the critiques, and the fundamental problems that brought the field to its knees. And third, we'll watch the cycle repeat. A brief new summer in the 1980s, followed by a second AI winter. Understanding this boom and bust cycle is not just a history lesson. It is perhaps the single most important piece of context for understanding the AI-driven world we live in today. It helps us separate the genuine breakthroughs from the marketing hype, and it gives us the wisdom to ask, is this current AI boom different, or are we just setting ourselves up for another winter? Let's begin. The Dartmouth workshop ends in 1956. The attendees, now funded and full of purpose, scatter back to their home institutions at MIT, Carnegie Mellon, Stanford, and they start to build. The optimism of this era, it's hard to overstate. These weren't just engineers debugging code. They saw themselves as digital architects of the mind, and their early successes were staggering. At Carnegie Mellon, two of the Dartmouth founders, Alan Newell and Herbert Simon, had already created a program called the Logic Theorist. This program wasn't just crunching numbers, it was manipulating abstract symbols. Given a set of logical axioms, it managed to independently prove 38 of the 52 theorems from the Principia Mathematica, a foundational work of logic. One of its proofs was even hailed as more elegant than the one published by the original human authors. Think about that. A machine wasn't just calculating, it was reasoning. Newell and Simon doubled down. They created a program called the General Problem Solver, or GPS. Its very name tells you everything you need to know about the ambition of the time. The GPS was built on a principle they called means-ends analysis. This is a concept that will be foundational when we get to episode 4 on search. The basic idea is simple. You have a current state. Say, I am in my apartment. You have a goal state. I want to be at the grocery store. The GPS would look at the difference between those two states, the distance, then it would consult a list of operators or actions it could take, like walk, take bus, or drive car. It would pick the operator that most reduced the difference. Maybe drive car isn't possible because the difference, I don't have a car, is a new problem. So it breaks that problem down. How do I get a car? Well, I can't. So I'll try take bus. This recursive goal-oriented breakdown. This was the general problem solver. And it worked for specific, well-defined toy problems, like solving logic puzzles or the Towers of Hanoi game. It was a remarkable demonstration that a machine could, in a structured way, mimic a human's conscious problem-solving strategy. While GPS was mastering abstract logic, other researchers were trying to get AI to understand language. This brings us to MIT and a landmark program from 1970 called SHRDLU. SHRDLU, created by Terry Winograd, was one of the most astonishing demos of the era. Imagine a virtual box filled with colored blocks, pyramids, and spheres. This was SHRDLU's entire world. A user could type commands in plain English, and a virtual robot arm would manipulate the objects. But it was so much more than pick up the red block. SHRDLU could understand context. You could say, pick up a big red block. The program would respond, okay. Then you could say, find a block which is taller than the one you are holding and put it into the box. Think about that. The program understood that the one you are holding referred to the big red block. It had a memory of the conversation. It could even answer questions about its own past actions, like, did you pick up anything before the cone? It looked like genuine understanding. The secret to SHRDLU's success, however, was also its greatest limitation. It operated in what researchers called a microworld. Winograd and his colleagues knew that the real world, with its infinite complexity, was just too hard. So they created an artificially simple, perfectly logical, and completely defined environment. In SHRDLU's world, there were only about 50 words that mattered. The rules of physics were simple and absolute. Within this tiny, sealed-off universe, language could be mapped directly to logic. The program didn't know what a block was, the way a child does. It only knew the logical properties of the object labeled block. This was a brilliant research strategy, but it was also a seductive trap. The stunning success of SHRDLU created an illusion of general competence. It led to a wave of optimism, a belief that scaling this up to the real world was just a matter of adding more rules and more words. This mistaking performance in a toy world for genuine intelligence, was a key seed of the coming winter. So, we have AI mastering logic. We have AI appearing to master language in a virtual world. But what about the physical world? For that, we go to the Stanford Research Institute, or SRI. Between 1966 and 1972, a team built Shakey. Shakey was a wheeled, human-sized robot with a TV camera, collision sensors, and a radio link to a massive remote computer. And it was revolutionary. It was the first general-purpose mobile robot that could reason about its own actions. You didn't give Shakey a step-by-step list. You gave it a high-level goal. For example, push the block off the platform. Shakey would then use its camera to build a logical model of the room. It might see the platform, see that it's too high, scan the room, locate a ramp, and then it would devise its own plan. It would formulate a subplan, push the ramp to the platform. It would execute that. Then it would formulate a new plan, roll up the ramp, and only then would it execute the original goal, push the block off. This was the first time a machine had ever autonomously connected perception, logical reasoning, and physical action. The software that powered its brain, called strips, the Stanford Research Institute problem solver, became a foundational technology for all future automated planning. Shakey captured the public imagination. Life magazine famously called it the first electronic person. It was the physical embodiment of the whole, good old-fashioned AI dream, that intelligence is, at its root, the manipulation of symbols according to logic. We've seen logic, language, and physical action, but there's one more demonstration from the golden age we must talk about, because its legacy is deeply unsettling, and it's the most relevant to our lives today. In 1964, at the MIT AI lab, a researcher named Joseph Weizenbaum created a chatbot. He named it Eliza. Weizenbaum's goal was the opposite of his colleagues. He wasn't trying to build intelligence. He was trying to parody it, to show how superficial a human-computer conversation could be. Eliza was, by today's standards, almost comically simple. It was a master of parlor tricks. It primarily operated as a Rogerian psychotherapist, a type of therapist that mostly reflects the patient's own words back at them as questions. If you typed, "I am feeling sad about my mother," Eliza would scan the sentence for keywords like mother. It had a pre-programmed rule. If input contains mother, respond with, "Tell me more about your family." If you typed, "My boyfriend made me come here," Eliza might respond, "Your boyfriend made you come here? That's interesting. It was just rephrasing your own statement." It was a simple script, a cheap trick. But something astonishing happened, something Weizenbaum did not expect at all. People loved Eliza. They confided in it. They poured their hearts out to it. They reported feeling heard and understood. Weizenbaum was horrified. He famously wrote about his own secretary, who knew it was just a program, who had seen the code, and she still asked him to leave the room so she could have a private conversation with the machine. Weizenbaum wrote, "I had not realized that extremely short exposures to a relatively simple computer program could induce powerful delusional thinking in quite normal people." This phenomenon became known as the Eliza effect. It's our deep, innate human tendency to project intelligence, empathy, and consciousness onto anything that mimics human-like communication. We are still living in the shadow of the Eliza effect today. Every time we feel a large language model understands us, Weizenbaum had stumbled upon a fundamental vulnerability in human psychology. So, fueled by the staggering successes of logic, GPS, virtual understanding, SHRDLU, physical reasoning, Shakey, and the illusion of empathy, Eliza, the leaders of the field, the founders from Dartmouth, began to make predictions, and they were breathtakingly bold. This was the peak of inflated expectations. In 1958, Herbert Simon declared, "It is not my aim to surprise or shock you, but there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly, until, in a visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied." In 1967, Marvin Minsky stated, "Within a generation, the problem of creating artificial intelligence will substantially be solved." And in 1970, Life magazine quoted Minsky as saying, "In from 3 to 8 years we will have a machine with the general intelligence of an average human being, by 1978. These were not charlatans. These were Nobel laureates, Turing Award winners. These were the brightest minds of their generation. They were also profoundly wrong. And that profound miscalculation, That gap between ambitious promise and technical reality is what triggered the first AI winter. The 1970s arrived, and the promises of the 60s were coming due, but the programs weren't scaling. The toy problems that the general problem solver could handle, they were just that, toys. The microworlds that SHRDLU lived in, they stayed micro. When you tried to apply these methods to a real-world problem, you ran into a brick wall that has haunted AI ever since. It's called combinatorial explosion. Let's go back to our analogy from episode 1. A problem is like a maze. A toy problem is like a maze in a children's coloring book. There are maybe 10, 20, 50 possible paths. A program like GPS could explore them all, one by one, and find the exit. A real-world problem, like translating a sentence or planning Shakey's route in a crowded changing room, is not a simple maze. It's a maze where every junction has dozens of new paths, and each of those paths has dozens more. In chess, there are about 30 legal moves from any given position. After your opponent moves, there are roughly 30 more. The number of possible paths, the number of possible games, isn't 50, it's 10 to the 120th power. That's a 1 followed by 120 zeros. It's a number larger than the number of atoms in the known universe. The early AI programs, they just stopped. They would grind to a halt, choked by the sheer number of possibilities. The methods that worked so well in the toy world were completely, utterly useless in the real world. This was the first great failure, the problem of scale. The second failure was even deeper. It was the problem of knowledge. It turned out that reasoning, like the logic theorist did, was the easy part. The hard part was common sense. AI researchers call this Morovitz's paradox. The paradox is that in AI, the hard things are easy, and the easy things are hard. It's easy to build a program that can prove complex logic theorems, something a PhD in mathematics struggles with. It is impossibly hard to build a program that has the common sense of a 4-year-old child. How do you tell a computer what wet means? Or that if you're holding a string, you can pull an object, but you can't push it? How do you explain that a glass of water can be in a room, but the room cannot be in the glass of water? SHRDLU never had to face this. Shakey never had to wonder if the block was heavy or fragile. The human mind is not just a logic processor. It's a vast, interconnected, inspoken database of millions upon millions of tiny facts about the physical and social world, all learned through years of lived experience. The AI researchers had no idea how to represent this common sense knowledge. How do you even begin to write it all down? They had built powerful engines, but they had no fuel. These two problems, the combinatorial explosion and the common sense knowledge gap, were theoretical crises, but the end of the golden age was triggered by something far more practical: money. The funding for the golden years came largely from military and government agencies, most notably DARPA, the Defense Advanced Research Projects Agency, and they were funding this research with specific goals in mind. One of the holy grails was machine translation. This was the height of the Cold War. The U.S. government had mountains of Russian technical documents, radio broadcasts, and reports. They were drowning in data they couldn't read. They poured millions of dollars into AI labs to build a program that could automatically translate Russian to English. And the early results, just like with Eliza, seemed promising. But language, it turns out, is not a simple substitution code. Language is ambiguous. The simple English sentence, "time flies like an arrow," could mean that time, the concept, moves quickly. It could mean that you should time with a stopwatch. Flies, the insects, in the same way you would time an arrow. Or it could mean that a specific kind of fly, a time fly, is fond of a particular arrow. Without a vast database of common sense and world knowledge, a computer has no way to disambiguate this. In 1966, the government had enough. They commissioned the Automatic Language Processing Advisory Committee, or ALPAC. The ALPAC report was an execution. It concluded, quite brutally, that machine translation was slower, less accurate, and significantly more expensive than just hiring human translators. It stated that there is no immediate or predictable prospect of useful machine translation. And just like that, the funding vanished. All government support for machine translation research was canceled overnight. This was the first domino. A second, even larger blow came from across the Atlantic. In 1973, the British government commissioned the eminent applied mathematician Sir James Lighthill to write a report on the entire state of AI research. The Lighthill report was an unmitigated disaster for the field. It echoed the problem of combinatorial explosion, criticizing AI for its utter failure to achieve its grandiose objectives. Lighthill argued that the field's successes, like SHRDLU, were limited to toy problems, and that its techniques would not scale to the real world. He concluded that the core bridge research, the part aiming for general intelligence, was a dead end. Following his report, the British government completely dismantled AI research in most of its universities. So, the funding for translation was gone. The funding in all of the UK was gone, but there was one more nail in the coffin, a theoretical one. Remember how we've split our curriculum. Part 2 is classical AI, the logic and search of the golden age, but Part 4 is diving deep into neural networks. Well, during the golden age, there was a competing idea, a smaller group of researchers who weren't inspired by logic. They were inspired by the brain. They were building perceptrons, the very earliest, simplest models of artificial neurons. We will dedicate all of episode 11 to this. This approach was a rival to the logic-based approach of Minsky and Simon. In 1969, Marvin Minsky, the same man who co-founded the MIT AI Lab, along with Seymour Papert, published a book titled simply Perceptrons. This book was a mathematical takedown. It was a brilliant, rigorous, and devastating critique. Minsky and Papert proved, mathematically, that the simple, single-layer perceptrons of the day were incapable of solving a whole class of problems. The most famous example, the XOR problem. XOR stands for exclusive OR. It means one or the other, but not both. Imagine a computer needing to learn this simple rule. If input A is on and input B is off, the answer is true. If A is off and B is on, the answer is true. But if both are off or both are on, the answer is false. It's a trivially simple logic problem. A human child can learn it in seconds. Minsky and Papert proved that a single-layer perceptron could not ever learn this function. It was a fundamental, mathematical limitation of the architecture. The book did speculate that more complex, multi-layer perceptrons might overcome this, but they guessed that training them would be computationally intractable. The impact of this book was immediate and absolute. It convinced the entire research community, and more importantly, the funding agencies, that the neural network approach was a complete and total dead end. Research into neural networks, which we now know is the foundation of the entire modern AI revolution, stopped. It just died for over a decade. So let's take stock. It's the mid-1970s. The golden age is over. The grand promises of human-level intelligence have crashed against the twin walls of combinatorial explosion and the common sense problem. The funding is gone. The Alpac report has killed machine translation. The Lighthill report has killed research in the UK, and Minsky and Papert's book has killed the other major paradigm, neural networks. This was the first AI winter. It was a winter in every sense. Funding was frozen. Labs shut down. Graduate students were warned away from studying AI, as it was now a toxic, failed field. The very term artificial intelligence became an embarrassment, a dirty word. Researchers had to rebrand their work, calling it machine learning, pattern recognition, or knowledge-based systems, just to get a grant. It was a time of deep disillusionment. The hubris of the 60s was replaced by a grim, cold reality. But winters do not last forever. The field, smaller and more humbled, regrouped, and in the early 1980s, a new summer began to dawn, but it was a different kind of AI. The researchers effectively said, "Okay, forget general problem solving. Forget the human-level intelligence of Minsky and Simon. That's too hard. Let's forget trying to build an artificial human. Let's build an artificial expert." This was the birth of expert systems. The philosophy was completely different. Instead of trying to create a program that could learn about the world, they would hard-code the world's knowledge into it. An expert system has two parts. First, a knowledge base. This is a massive database, not of common sense but of specialized expert knowledge. A team of knowledge engineers would sit down with a human expert, say, a geologist, for months. They would painstakingly extract every if-then rule that geologists used to do their job. If the rock strata is limestone and there is a fault line, and we detect trace hydrocarbons, then there is a 70% probability of an oil deposit. They would load thousands of these rules into the knowledge base. The second part was the inference engine. This was basically the reasoning part, a program that would chain these if-then rules together. A user could query the system, and the inference engine would walk through the rules to arrive at an answer, often with a confidence score. It was, essentially, a digital clone of a single, hyper-specialized expert. And unlike the general problem solver, these worked, and they made money. One of the first and most famous was a program called XCON, developed for Digital Equipment Corporation, or DEC. In the 1980s, DEC sold high-end VAX computers, but every customer order was unique. Different memory, different processors, different storage, all with complex compatibility rules. Configuring these orders was a nightmare for the human sales team, and they made millions of dollars in errors. XCON was an expert system with thousands of rules about VAX computer components. It took an order, and it correctly configured the entire system, ensuring all parts were compatible. It was not sexy. It wasn't general intelligence, but it saved DEC an estimated $25 million a year. Suddenly, AI was back. Other systems followed. Mycin, a program that could diagnose bacterial blood infections with a higher accuracy rate than junior doctors. Prospector, an expert system that successfully predicted the location of a multi-million-dollar ore deposit. A new gold rush began. This wasn't the blue sky research of the 60s. This was commercial AI. A new industry sprang up building specialized hardware called Lisp machines. These were computers custom-built, from the transistors up, to run the Lisp programming language that these expert systems were written in. Companies like Symbolics and Lisp Machines Inc. were the darlings of Silicon Valley. And the hype cycle started all over again. This time, the fear of being left behind went global. In 1982, Japan's Ministry of International Trade and Industry announced the 5th-generation computer systems project. This was a 10-year, nearly billion-dollar national initiative to leapfrog the United States and dominate the next era of computing, and their entire bet was on AI, specifically on building massive parallel computers designed to run logic programming and expert systems. The US and Europe panicked. The AI race was on. DARPA and other agencies, terrified of being beaten by Japan, started pouring billions of dollars back into AI research. The AI summer of the 1980s was in full swing, but as you might have guessed, it was built on a familiar, unstable foundation. The crash, when it came, was even faster than the first one. What went wrong this time? The expert systems, they had a fatal flaw. They were brittle. What does brittle mean? It means they operated perfectly, within their exact, narrow pre-programmed domain. But the instant they encountered a problem or a piece of data that was not in their rulebook, they didn't just get the answer wrong. They broke. They fell apart completely. They had zero flexibility, zero common sense. Ask Myson to diagnose a blood infection. It's brilliant. Ask it what a fever is, and it would have no idea unless a human had explicitly programmed the rule. Fever is a high body temperature. It couldn't learn. It couldn't adapt. And they were insanely expensive to maintain. Imagine your expert system has 50,000 rules. Now you need to add rule number 50,001. Does this new rule accidentally contradict Rule 7422? Does it create a logical loop with Rule 23,000? As the knowledge base grew, it became a tangled, unmanageable, undebuggable mess. This was the software crisis of expert systems. They simply collapsed under their own weight. At the very same time, the hardware market collapsed. Those beautiful, expensive, specialized Lisp machines that everyone had bought. By 1987, new, cheaper, general-purpose processors, like the ones from a new company called Sun Microsystems, had become so fast that they could run Lisp programs faster than the specialized machines. Why buy a $1 million custom-built race car when a $50,000 souped UP sedan could now beat it around the track? The entire Lisp machine market, a multi-billion-dollar industry, vanished, almost overnight. And what about Japan's 5th-generation project? It was a spectacular, public failure. The logic-based approach they had bet everything on turned out to be a dead end for the kinds of problems they wanted to solve. The hardware was impressive, but the AI just wasn't there. By the early 1990s, the project was quietly disbanded. With the collapse of expert systems, the death of the Lisp machine market, and the public failure of the 5th-generation project, the money vanished again. This was the second AI winter. This one was, in many ways, worse. The first winter was the death of academic innocence. The second winter was the death of commercial viability. AI wasn't just a research failure, it was now a business failure. The term AI winter was actually coined in 1984 in the middle of the 80s boom by researchers who had lived through the first one. They were standing at a conference watching the hype, and they turned to each other and said, "This won't last, the AI winter is coming." And it did. From roughly 1987 to the mid-1990s, and arguably all the way into the 2000s, AI was once again a wasteland. Funding was non-existent. AI was the punchline to a very expensive joke. Now, this brings us to a critical junction, and it's time to correct a major misconception. The common story, is that AI died in the 1990s and was only reborn around 2012, that for almost 20 years nothing happened. This is completely wrong. The hype died. The funding for artificial intelligence as a brand died. The commercial industry for Lisp machines and expert systems died. But the research, the real research, it just went underground. Remember those neural network researchers who were exiled by Minsky and Papert's book back in 1969? They never actually stopped. Throughout the entire first winter, and all through the 1980s expert system boom, a tiny, dedicated, and very unfashionable group of researchers kept working on the perceptron idea. People like Geoffrey Hinton, Jan LeCun, and Yoshua Bengio, names that are now synonymous with the modern AI revolution. In the mid-1980s, they had a massive breakthrough. They figured out a mathematically efficient way to train multi-layer neural networks, the very ones Minsky and Papert had dismissed as intractable. This algorithm is called backpropagation, and it is the absolute core engine of all modern deep learning. We will dedicate an entire episode, episode 13, to understanding exactly how it works. During the second AI winter of the 1990s, Jan LeCun used backpropagation to build a neural network that could read handwritten zip codes for the post office. It was a huge success, but no one called it AI, they called it pattern recognition. So, while the world was convinced AI was dead, these connectionist researchers were quietly, stubbornly, building the engine of the next revolution. They were just waiting for two things that the world of the 80s and 90s simply did not have. What were the two missing ingredients? First, data. Neural networks, as we will learn, are hungry. They learn by looking at millions, or today billions, of examples. In the 1980s, where were you going to get a million labeled images? You couldn't. The entire dataset for a problem might be a few thousand painstakingly collected by graduate students. And then, the internet happened. Suddenly, the world was digitizing itself. People were uploading billions of photos to Flickr and Facebook. We were creating trillions of words of text in blogs and websites. For the first time in history, we had the fuel, massive web-scale datasets, to train these hungry new models. A project called ImageNet was launched, which hand-labeled millions of images from the web, creating the perfect training ground. The second missing ingredient, compute. Backpropagation, the learning algorithm, is a lot of math. Specifically, it's millions and millions of simple matrix multiplications. In the 1990s and 2000s, another industry was booming, video games, and video game players demanded realistic 3D graphics. To do this, companies like NVIDIA built graphics processing units, or GPUs. A GPU is a very special kind of chip. It's not a generalist like your main CPU, which does one or two complex things at a time. A GPU is a specialist. It's an army of thousands of tiny simple processors that all do one thing in parallel. That one thing, the exact kind of matrix math needed to render 3D graphics. And in one of the happiest accidents in the history of technology, it turned out that the exact same math used to render 3D graphics is the exact same math needed to run backpropagation on a neural network. The pieces were all on the board. By the late 2000s, we had the theory, backpropagation, refined for decades in the winter. We had the data, the internet and ImageNet, and we had the compute, GPUs from the video game industry. The stage was set for the current AI spring. The starting pistol was fired in 2012. It was the annual ImageNet competition, a contest to see which computer program could best recognize and label objects in photos. The classical AI approaches, the non-neural network ones, had been slowly improving year after year. Then, in 2012, a team from the University of Toronto, led by Geoffrey Hinton, the same man who had worked on backpropagation in the 80s, entered a model called AlexNet. It was a deep neural network. It ran on two standard NVIDIA gaming GPUs. It didn't just win the competition, it annihilated it. The error rate for the reigning champion was 25.8%. AlexNet scored 15.3%. It wasn't just a small, incremental improvement. It was a phase change. It was a signal to the entire world that the 40-year-long winter was over. The neural network approach, the one killed by Minsky in 1969, was, in fact, the only path forward. That moment, the AlexNet moment, is what separates the history of AI from the present. It is the direct ancestor of the CNNs that power your phone's camera, the RNNs that power translation, and the transformers that power the generative AI you're reading about every single day. And we will cover all of it. So, let's summarize what we've learned today. We've charted a truly dramatic roller coaster. We saw the golden years of the 1950s and 60s, a time of boundless optimism where programs like the General Problem Solver, SHRDLU, Shakey, and ELIZA made intelligence seem imminent. We saw that optimism crash into the first AI winter, triggered by the combinatorial explosion, the common sense problem, and the devastating trilogy of reports, ALPAC, Lighthill, and perceptrons, which collectively starved the field of funding and ideas. Then we saw a new boom in the 1980s, the rise of expert systems, a more pragmatic commercial AI. We saw this boom collapse into a second AI winter, as these systems proved too brittle, too expensive, and the hardware they ran on became obsolete. And finally, we saw the seeds of the modern boom quietly cultivated during the winters. The development of backpropagation, combined with the two game changers, massive data from the internet and parallel compute from gaming GPUs, which set the stage for the 2012 AlexNet revolution. So what is the lesson of the AI winters? It's not to be a cynic. It's not to believe that this time is just another boom before another bust. It's to be a scientist. It's to be an educated citizen. It's to learn how to separate the engineering from the hype. The leaders of the Golden Age promised human-level intelligence and failed. The leaders of the 1980s boom promised digital experts and failed. The current revolution is built on a different foundation, one of statistics, data, and massive computation. It has already delivered far more than those previous eras ever did. But understanding this history, understanding the failures, is what gives us the critical lens to ask the right questions. It gives us the humility to see the profound limitations that still exist, and the wisdom to recognize the genuine world-changing breakthroughs that are happening right in front of us. And that is why we spent an entire episode on this, because this history, these cycles, they define our curriculum. The current AI spring is built on the neural network paradigm. That's part 4, V and V of our course. But that first paradigm, the good old-fashioned AI of the golden years, the logic and search approach of Newell and Simon, it didn't die, it just found its proper place. It's still the foundation. It's the set of ideas we use to structure a problem so that an AI can solve it. Before we can get to the magic of deep learning, we must first build a foundation in classical AI. And that is exactly where we are going next. We are now leaving Part 1, the dawn of AI, and officially entering Part 2, the pillars of classical AI. In our next episode, we are going under the hood of the general problem solver. We're going to bypass the hype and learn the fundamental algorithm that powers everything from your GPS navigation to the AI in a video game. We're going to explore problem solving as search.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.